Okay, let's go ahead and get started here. Today, we're going to be actually writing some code for the first time. And we're going to look at how to implement some concurrency in Python. But before we dig into that, there's one thing I want to quickly talk about here. And that is, today we're going to look at, first off, effective orderings, meaning that when you have two sequential processes, or maybe 3 or 4, however many you have those effective orderings that come out. So if they're concurrent, then those things can overlap. So if they have instructions in them, like let's say we have 3 instructions and 3 instructions, it's not always one before the other, or this one before that one. That there can be all of these effective orderings where they overlap in different ways. And that is where the non-determinism from concurrent execution comes from. So we're going to take a quick look at that, and then we're going to look at concurrent programming in Python. Now we're going to be doing a lot more in Python than we're doing today. We're going to look at kind of one kind of basic method initially today, and then we're going to dig farther and farther into that as the semester progresses. So we're going to spend some time doing stuff in Python. If you're not familiar with Python or don't have it installed on your machine, it's free. It's free in 2 ways. It's not corporate owned. It doesn't cost anything to install it and use it. It's available on all kinds of different devices, all the way from mobile devices and microcontrollers all the way through PCs and Macs and Linux. So whatever platform you're using, you can use Python on that. And then at the end, we're going to take a quick look at Lab 1, and then you should have some time today to actually work on Lab 1. All right, so let's go and get started. So first off, concurrency and non-determinism, quick review of that. If we have 2 sequential processes, we'll call them A and B, and they are executed concurrent with one another. So A concurrent B, here's our concurrency operator here being illustrated. So A concurrent with B, that means the processes are allowed to overlap their execution. And that ability for them to overlap means that they have a lot of different effective orderings possibly as they're executed. So when we run it, we don't know, is it going to be like this? Is it going to be like that? Is it going to be like that? Is it going to be like this, that? There's a whole bunch of ways that those could overlap. And the more instructions we have, the more effective orderings we get. And that's where it gets a little bit scary, is when we test the code, it might look like it works, but there could be one of those orderings or some subset of those orderings that we get unlucky, that are bad, they produce a wrong result, they lock up, whatever. And we'll look at those kinds of errors a little more later on, not today, but later on in the semester. But let's look at what that means to have 2 sequential processes. So we have processes A and B, and each of them have N and M instructions respectively each. So in other words, A might have 3, B might have 3 if N and M were 3, but A could have 5 and B could have 12. So we could have a different number of instructions for each. They don't always have to match. We could have 2 and 5 or 60 and 1,000. It doesn't matter. It's 2 different numbers. And in fact, we could have more than 2 processes, as we'll see a little bit later on. So let's say we have A and B, and each have 3 instructions. So in other words, N is 3 and M is also 3. So in other words, here's what those would look like. A is A1, A2, A3. Those are kind of the low-level instructions, the CPU instructions, if you want to think of them as that. So this has 3. This also has 3. They're both sequential. So the parts of A can't overlap the parts of A. The parts of B can't overlap the parts of B. But if I have A concurrent with B, then we could interleave or overlap those instructions of this execution stream with that execution stream. So the question is, how many effective orderings are there with 3 and 3? Well, we know there's going to be more than one, because even if we don't allow those to overlap, we could have A and B. We already have 2 like that, but then we could have the first instruction of A and then all of B in the second and third. We could have the first and second instruction of B, and then the third. We could have the first instruction of A and the first instruction of B and the second and third instruction of A. So it could overlap like that. There's a whole bunch of those. So let's take a look at how that would look. So here, starting out, the first one is, well, we did all of A and then we did all of B. But we could overlap them and do the first 2 of A, 1 of B, the third of A, and that one. And then it could be the first 2 of A, the first 2 of B, and then the third of A, the third of B, and so forth. So this works through 10 of them. And are there more? So we got 10 just listed there. And I kind of did that by marching the A across, and the B's then moved back. So the A went all the way to the end. But then we had one where two of them marched across, and then the A went to the end, and then I moved the two of them. There's the A at the end, and then I moved the two of them ahead again, marched the A across, and so forth, and now I'm at the end. But we're not done yet, because notice all of these had A1 as the first symbol, so we have all of the ones where B1 is the first symbol as well. And to get those, I just basically copied all of these, but switched the A's and the B's, so this is all of them with B starting first, and those are all okay. And here are these 20 orderings, and you'll notice that with the 20 orderings that we have here, some of them may be more common than others. For example, that the ornamental garden problem that we looked at previously, the ones where they don't overlap at all, like this one where A went first and then B, or the one where B went first and then A, like we have over here, those might be the most common, because the only time we're going to get any real overlap is when somebody leaves at the exact time somebody comes in, and then it will be one of these. And there might be some of these that are okay. There might be some of them that cause a problem. And that's the problem with concurrent programming, is testing it. If you just test the function with like a unit test, you'll say, well, let's try enter. Yeah, that worked. Let's try exit. Exit worked. But then you run them concurrently. It mostly works. And then every once in a while, you'll get unlucky and get one of these ones down here that causes a problem. Now notice with just 3 and 3, we get 20 instructions, or 20 possible orderings of instructions. Now, so if A is concurrent with B, there's no way to be sure which of these orderings would occur. So we don't know which ordering might occur at any given time when we're executing these concurrently. And some of them, like in the case of the ornamental garden problem, this one or this one might happen almost every time, unless we get unlucky and have one where the two events happen at the same time and they overlap, and then it could be any one of these other ones. So they're not all equally likely. So if you had a concurrent program, a concurrent solution for something, it's like, what are the odds we come up with this ordering down here? It's not really 1 in 20. It could be much less than that, because these ones might happen much more frequently than this one does. Okay, so let's look at a few examples here. So if we were to, instead of having 3 and 3, if we had different numbers of instructions, like 1 and 1. So if I just have 1 and 1, there are two orderings. The A comes first and then the B, or the B comes first and then the A. If I have 1 and 2, there are 3 orderings. A, B1, B2, so A1, B1, B2, B1, A1, A2, B1, B2, A1. So you just move the A through, and then you have all the possibilities. What about 2 and 2? 2 and 2 gets 6 orderings. 1, 2, 3, 4, 5, 6. 2 and 3 gives 10 orderings. 3 and 3 gives 20 orderings. That's what we wrote all those out. That's what all these were back here. And what does 3 and 4 yield? And I'll let you think about that one, but I'll give you a hint. It's more than 20. It's more than 30. And the reason I'm not going to give you the exact answer for that is one of the things that I want to do here. We'll talk about that in a second. But I'll leave that off, and on the next page I'll talk about why I'm not giving you the answer for that. But if you look at this, notice that this kind of is increasing exponentially. It went from 2 to 3, so it raised by 1, but then it doubled. And then it didn't quite double, but it went up to 10, and then it went to 20. And then 3 and 4, I said it would go up to something more than 30. So it's not growing in like a geometric progression. It's growing in this kind of sort of exponential progression. So also, how could we extend that? Could we extend that to more than 2 processes? Well, yeah, we could have 3. So if we had 3, 3, and 3, there are all a lot more ways those could overlap as soon as you have a 3rd one, or a 4th one, or a 5th one, or a 10th one in there. Okay, so here's what it would look like with 3 processes. You just have, here's 3, 3, and 3. With those 3 instructions and 3 processes. So with A concurrent B concurrent C with 3 instructions each, that yields almost 1,700 possible orderings with just those simple processes that we're showing up here. Okay, so here's why I didn't tell you the answer to that, and here's a bonus challenge. You'll get 10 bonus points on the midterm exam for the first student to email me that formula and produce, or the formula that produces the effective number of orderings given processes of N and M instructions. In other words, I want you to make a function. This is not a function like programming. It's just a formula, basically, that takes N and M and produces that number of orderings. So if you fed in 3 and 3, if you fed function 3, 3, it should put 20 out. If you fed in 1 and 1, it should put out 2. And it should work for any number. So it shouldn't just do the ones that I showed over there. It shouldn't be like a big if else or something stupid like that. It needs to actually be a generalized formula to produce the effective number of orderings. So once you have that answer, email it to me. The first correct response gets the bonus points. And for an additional 2 points, if you extend your formula to work with any number of processes like this, 3, 3, and 3, then you'll get an extra 2 bonus points. If the person who got this correct did not get this, then these are still available for someone else, the second or third or fourth person to submit something. Okay, so again, the way I'll grade that, send it to my Shawnee email address. I'll use whichever one is the received most or first that is correct is the one that will actually receive those 10 bonus points. Okay, now let's dig into what we're supposed to do today, and that's a little bit of Python threading. And what we're doing with Python threading is we're going to look at how to make threads, we're talking about what threads are, and then we're going to actually look at the code to do that. All right, so Python has a standard module that allows us to make threads. And you might say, well, what's a thread? We've been talking about processes. And threads are like processes in that they allow us to have parts of our program that run concurrently, meaning that are allowed to overlap their execution. And threading allows execution of 2 or more threads concurrently. So in other words, it's not just you have 2, you could have 3 or 5 or 100 or however many you want. But one thing to note in Python, and this is what distinguishes threads from completely separate operating system level processes, a thread shares the interpreter with the other threads that are spawned in that application. And because it shares that interpreter, it also has the same kind of global variable memory or global object space to access global variables to. So think about it like a separate thread of execution or a separate thing where it can run code independent in another thing concurrently with the main thread and then any other ones that get spawned. But they share the same memory space and they share the same interpreter. It's one interpreter. Now, later on, we're going to look at another module called multiprocessing that allows us to write code that is process parallel, not just thread parallel, meaning that could have a Python interpreter in one process, another whole separate Python interpreter in another process, and they can run stuff concurrently, even on separate processors or cores of processors, and we're still going to get them to communicate with each other. But now, think about threading like it is still the CSP model, so each of the threads is sequential but running concurrently. We're just using the word thread to distinguish them from processor-level processes that have their own memory. They're separated or isolated from other processes. Threads run all in the same program, in the same application space. They all have the same global memory, which can make some things a little more convenient. Okay, so let's look at a quick overview of how you use the threading module. First, you have to import it. It's a standard module, so if you have installed Python, you have it. You don't have to download it. You don't have to install anything. You just say import threading. After you've imported threading, you can create a thread object by saying threading.thread. Notice the capital T, like most classes, we call it with that. And then to specify what we want that thread to do, we give it a function name. So you say target equal, and then give it the name of a function. So in other words, what's going to happen is whatever function name I put here And whatever arguments I want to pass to that function, I put here an args equal. That would be a tuple that goes there. So parentheses with things separated by commas in them. But essentially what you're doing here is when you say target equal, give it a function name, args equal that, it's going to spawn that function in its own thread. In other words, it's like calling that function, but it's calling it in its own thread. And then, but it doesn't do it yet. This just creates the thread object that's ready to do that. It's ready to start that thread up. And then down here, you can say thread1.start. If you have another one, you can say thread2.start. Now, what's interesting is now these two threads are running concurrent with the main thread that is still running the code down here. So when I get down to here, I can still have 3 threads running. I can have thread 1 running, thread 2 running concurrently, and the main thread that's down here running concurrently. So start starts them up, starts them executing, and what join does is that waits for them to finish and complete before it goes on. So in other words, you can see this code branches out into, it's coming along with one thread, it makes those threading objects, and then it hits thread1.start. Now I have 2 threads running concurrently. I hit the main thread, hits thread2.start. So this one kind of pushes over, and now I have 3 threads running concurrently. And then what the joins do is if the main thread gets to the bottom of that, first it'll wait for thread 2 or thread 1 to finish, and then thread 2 to finish, and then they'll go back on. So you can see why that's called join, because it's like these, we have the one thread, it branches out into 2, branches out into 3, and then they come back together again into 1. It's kind of forking or branching out, and then collapsing back down to 1 thread. All right, so let's try that on a simulation of the ornamental garden problem. And so I'm going to actually go ahead and write the code for that. So what we're going to do is go ahead and switch over to a Python interpreter. So let me do that first. So give me just a second here to launch a Python interpreter. And I'm going to go ahead and use idle for this. It's not a great development environment, but it's the one that comes with Python if you download it. And so you don't need to install or configure some other tool. You can just use that. And let me switch the screen over so you can see what I'm doing here. And let me move the window. Let me resize it so we don't have stuff scrolling off the bottom. And let me just resize that a little bit better. There we go. All right, now I'm going to do File New. I'll make that so you can see it as well. Okay, so now we're ready to write the code that we want to write. Oops. Oh, let me move that out of the way. Hold on. Okay, so what we're going to do is I'm going to put a comment here. And when you turn in your assignments, oh, hold on. Can you see? Yeah, okay. So when you turn in your assignments, make sure to put a comment block at the top of your code. So here, so basically when you have your comment block at the top, you should put the class. And the section number, 01 if you're in the early section, 02 if you're in the later section, whatever. So I'll just say 01. And then you should put in what lab it is. In our case, we're not going to put that in because this is just example code. And you should also have your name in here. And actually, let's put the name first. And so if it's a lab that has multiple parts, like there's a part 1, part 2, part 3, or part A, part B, part C, put part A or part 1. If it has subparts like 1A, whatever, just make sure I know what lab it is. So here, this is just none. This is just example code. But I want you to be familiar when you turn something in, make sure you have that comment block at the top. So when I grade it, I know what lab it is, what it is you're trying to turn in. And so forth. But minimum I need your name, the class, and section, and what lab number it is. Okay, now onto the code. So here, for our example code, we're going to import threading. Now, import threading, just like we did there, is the reason that we're doing that is because the threading module, even though it's part of the Python distribution, it is not automatically imported. Just like if you're used to Python random, you want to make random numbers, you have to import random. Or if you want to have 2D graphics, import Pygame. Except the difference between threading and Pygame. Threading, you don't have to download and install or use pip to install it. It already exists if you have Python. All right, so import threading. Now the next thing that we're going to do here, remember, is we want to make a couple threads. So we talked about how to do that. So we said basically, I'll just call them T1. So T1 equal threading dot thread. And when I say threading dot thread here, we want to say target equal, and we want to put a function name here. But I'm going to put question marks there for right now because we don't know what function name we want. So we have to define that function before we can make the thread of it. And here for arguments, if we're not passing any arguments to it, we can just leave off the args thing like that. So threading 2 is going to be the same. Now let's look at this threading 1 first. So what we're going to have, the way I'm going to simulate this, I'm going to make an enter gate function. And inside of here, I want this to change the count. So the first thing here, for I in range. And the range I'm going to put here is, I'm actually going to define a variable. So I'm going to say num people. And since I'm defining that, I'm going to define it, or using that, I'm going to have to define it up here. So num people equal, here, let's put 10,000 for right now. So we're going to have 10,000 people come through this enter gate. And inside of this loop, I'm just going to say count plus equal 1. Now, count needs to be a global. And so to deal with that in Python, we're going to need to make that variable. So up here at the top, I'll say count equals 0. So when we start out at the beginning of the day, nobody is in the garden. Count is equal to 0. Now, to make that a global that we can access inside of this function, I just have to allow that to be accessed. So I'm going to say global count. And that's the entirety of my enter gate function, or those few lines right there. Count plus equal 1. And we're repeating that, in this case, 10,000 times. We have 10,000 people entering the garden in our simulation here. And let's do the same thing for exit gate. Except it's people leaving. So looking at this code, it seems like it would make sense. We're going to have 10,000 people enter. We're going to have 10,000 people exit. At the end of the day, it should be 0. So here when we're making our thread, let's make one for enter gate. One thing to note, that's don't put parentheses there because that's going to try to call that function. We don't want to call the function. We just want to specify it because it's not going to get started until we do t1.start. All right, so we need a thread 2 as well. So I'm just going to copy and paste. And you could follow along here if you want to. Pause it, install Python, make sure that works, and then follow along. So try this with me here. So we have one thread for enter gate. We have one thread for exit gate. And now what I'm going to do is I'm going to start those two threads just like we did in that little example code. So t1.start. So we're starting thread 1. t2.start. That's starting thread 2. Now I'm going to print out a message here and say threads are running. And now what I want to do is I want to wait for those threads to complete. So we're waiting for them to complete. So to do that, I'm just going to do t1.join and t2.join. And now at the end, I'm going to print out a message and say thread's done. And now let's print out what the count is. So we're just printing out count there. Okay, so let me rearrange this code a little bit. I'm going to go ahead and move this count equals 0 down here to put it with that. All right, so just to look at what's going on here. So the count is 0. We start both threads, and actually we could do count equals 0, I suppose, right there. So we set the count to 0. We start both threads. 1,000 or 10,000 people enter. 10,000 people also leave, but notice those are threads, so those are running concurrently. So we have 10,000 people entering at the same time, 10,000 people are leaving. And at the end of the day, once all 10,000 people have come in and all 10,000 people have left, we say that the threads are now done. There should be 0 people left in the garden. So let's try it and see what happens. So to try it, I'm going to do F5 to save it. And I'm going to call it garden1.py and save that. Now I ran that and it looks like it worked. So as a typical programmer, you're like, hey, 10,000 people came in, 10,000 people left. I had 0 left in the garden. That worked great. And let me run this multiple times. So let me make this a little smaller here so you can see that as I output that. And let me make this one a little smaller this way. We're going to run this multiple times here. And if you're not used to idle when you're in this window, you can just hit F5 to run it. And notice it looks like this works. I'm getting 0 every time. No problem at all. Works great. 10,000 people come in, 10,000 people leave. And you might think that works great. It's worked every time. I've tried it 10 times. It's never failed. It's got to be 100% accurate. So now let's say our next simulation, what happens if we have 100,000 people? Let's run that one. Now somehow we have negative 47,411 people in the garden. So 100,000 came in, 100,000 left. Somehow we have 47,411 more people that left than came in. Let's try it again. Now we had 1,240. Let's try it again. That time it worked great. Got 0. Negative 4,510, 0. 0 worked great twice in a row, 3 times in a row. Negative 65,989, 0, 0, 0. Oh, we got 3 good runs in a row. Now we have 52,396 people that came in that never left, according to our counter. So you'll notice that just from this simple program, you can kind of start to see some of the dangers of concurrency. When we tested it with 10,000, looked fine. Looked like it worked great. But then when we switched to 100,000, now we have all these weird numbers that are off, and not just a little bit off. They can be off by quite a bit. And you might ask, like, why? Why is it off by so much instead of just a little bit? And the reason for that is pretty simple. The reason for that is that the way that threads get scheduled and run in the Python interpreter is that it runs them, it gives one of them permission to run, and it runs them for a while. It says you can run for a little while. And what does that a little while mean? It means there's a certain amount of time they're allowed to have the processor until one of 2 things happens. The time expires and the processor is taken away from them and given to another thread to run for a while. Or some I/O event happens, the disk drive needs to read something, it needs to stop for some I/O for some reason, and then it might get taken away and scheduled for to someone else without the time expiring. But generally in this case, we're not really typing anything in or having any other I/O, so it's really just the time expiring. Although there could be operating system level things that take away the thing. And the reason why the time is given in blocks like that, called the time quanta, or the time quantum is how long it gives it, is that's to make the operating system or the system more efficient. Like, for example, if it was constantly like moving it between one program and the next and one and the next, it's more efficient for it to do a chunk of work for a while and then switch and do a chunk of work while. So think about that at home too. If you're trying to, check your mail at the same time you're talking on your phone, and you're, say, like, one word, run to the mailbox, get one letter, say another word, run to the mailbox, get another letter, say one more word, run to the mailbox, get another letter, run back to the phone, say another letter or another word, then you'll notice that you're spending all your time running back and forth doing stuff. It would be better to say, hold on a second, I'm going to check my mail, put the phone down, run out, sort the mail, go through it all, and come back and say, now I can have a conversation. Say, oh, my microwave went ding, hold on a second. Mess with the stuff in the microwave, come back. So it's more efficient to not switch off rapidly. But if you didn't switch off at all, then the stuff in your microwave could burn, or the person on the phone might think you disappeared and you couldn't make headway in your conversation. So the idea here is that when we switched from 10,000 to 100,000, suddenly we're probably exceeding the time quanta that one of the threads was allowed to have the thing. So at 10,000, there's still a possibility, though, based on I/O events, that this could give us a wrong number. It's just lower because it's likely we're finishing it in one entire chunk. But as soon as I make this 100 or 100,000 up here, well, in theory, yeah, that's 100,000 or a million. Now we start getting crazy values back to 100,000. But sometimes it does work. Sometimes it's fine. Sometimes it's not. But there still is a probability, even with a smaller number, that those things could still get interrupted and have things in a way. And the reason why these are so far off is one of them has picked up the number and then gotten interrupted, and the other one comes in and changes it and restores it, and then that one writes over the top of that, and we lose that entire block or a bunch of them rather than just one single one. Now, as we'll see in today's lab assignment, there is a way to kind of get it to artificially kind of give up control to more emphasize that failure, and that's by putting a little tiny sleep instruction around the different parts of what we're doing to make it more likely to get interrupted. And the place where it has to get interrupted to cause a problem here is around this inside this critical section. Picking up, for an order to have count plus equal 1, we have to pick up count. We have to get the number 1. And in Python, the Python interpreter, it's a stack base. We have to pick up count, push it on the stack, pick up 1, push it on the stack, issue an add operation, which pops both of those off the stack, and then push that back, take that result and put it back into the count variable. So we have these like a few steps: push, push, add, store. And that happens every time. In this other one down here, push, push, push the count, push the 1, perform the add, or perform the subtract, and then store that. So we basically have those kind of 4 instructions that are running in each of those that cannot be interrupted while it's doing that. Now the loop part, that'd be fine for that to get interrupted, especially since this I variable and that one are totally different. Okay, so that's that example code, and you can see that non-deterministic behavior. I'm not importing random, I'm not using a random number generator, but when I run this program, sometimes it works, sometimes it doesn't. Sometimes it fails catastrophically, like we see there. And if all I did was ever test this on smaller numbers, I might never see that. I might not. Okay, let's switch back to the presentation. So give me just a second here to switch back to that. Oops. Okay, so now we're back to the code. Here's the code we wrote. And again, I want to point out how you do this. So you make a function called whatever you want it to be called. In this case, enter gate. Here's another function called exit gate. Those become the targets of our threads. So this thread says, hey, when I start, call this function. And notice I left off the args equal part here. We're not passing any arguments to this, so we can leave those off. If we did have arguments, we would just add comma, args equal, and then put a tuple, which is a list of values separated in parentheses, or in parentheses separated by commas. And then we start the threads, join waits for them to finish, and then we print out our answer. Now, if we didn't have these joins here, I'd get an even different result because I'd print this out before those threads had finished. I'd say, how many people in the garden? I'd probably say 0 because we had just started these threads. Might say some of them may have entered or exited. We don't know. But note that we have 3 threads running while this is going. As soon as these are done, that collapses back into just the main thread. And then we print out how many people are in the garden. Okay, so now we're ready for lab 1. So let's take a quick look at that lab assignment. And then I'm going to give you the remainder of the time today to actually work on that. And that lab assignment is similar to what we just did with this program here, the ornamental garden problem, except it's a different problem. And this is another one that you should be able to, or hopefully relate to, maybe even more than the ornamental garden, which seems a little contrived. But this one is actually one that could be important for you to understand. All right, so let's switch over to that. Okay, so this is lab 1. This is worth 20 points. But essentially what you're going to do is you're going to make this bank account class. You're going to make an instance of that. And then you're going to withdraw money from that by getting the balance from it, changing the balance, and then setting it. So here's a bank account. The things you can do with this bank account is internally it stores a balance. And then notice that I have this, it also has a transaction log that's part of it that has stuff appended to it. And then down here, I have 2 methods. I have get balance, which basically just says read the balance into this temporary variable. And then do a self.transaction append what the current balance is. Somebody called get balance, so we're reporting that they got it. And then we're returning temp, which was the value that was stored in self.balance. And then you'll notice set balance does the opposite. Set balance says we pass it an amount. What it does is it does self.balance equal amount, just sets it, and then it adds to the transaction log just like get balance did. So this makes sense if you just think about it as a single threaded program. When you get it, you read this and return it. When you set it, you take the variable that was the parameter that was sent in and you set it to that. And then to do a deposit or a withdraw, a deposit would basically just be get the balance, add some amount to it, and then restore it by doing set. And a withdraw would be get the balance, subtract some amount from it, and then put it in there. So this is the kind of thing that would happen when you use an ATM machine. You take out, I don't know, $100 as a withdrawal. It gets your balance. It subtracts the 100 from that, and then puts the balance back in your bank account. And it adds something to the transaction log that said, hey, you went to an ATM machine and you took out $100 cash. So that's kind of what we're doing here with this transaction log thing. Okay, so in addition to those methods that we had above, I want you to add a couple additional methods down here for withdraw and deposit. And those withdraw and deposit, what those are going to do, it's going to get the balance. So with withdraw an amount, you're going to say get the balance using get balance, subtract the amount, and then restore it using set balance up here. So we get it, we subtract the amount that was passed into here, and then we use set to set it. And then we're also going to add this transaction, withdraw a certain amount, when we call that. So then we're also going to make a deposit, which works the same way. The only difference is it gets it and adds the amount and then restores it. And now what we're going to do is we're going to create a program that tests this by starting out with $1,000 initially. And then sequentially, we're going to deposit 500, withdraw 50, withdraw 10. So in other words, 1,000 plus 500 would give us 1,500 minus 50, which would give us now, 1,450, and then minus another 10, 1,390. So we should have 1,390 all at the end of the day when this is done. And you might ask, like, what are all these sleeps doing in here? And those are for two things. One is to get around the time quantum thing that we talked about earlier, but this is also here to kind of simulate the amount of time it might actually take to access that record. So when you say get balance, it's going to say, okay, I got to look up this thing in this database. I got to get that value into memory. And this would be like the time it would take to contact the logging system and add this thing here. So these are kind of to help the simulation be a little more realistic, but also it's so that these don't all run so fast that we don't see anything wrong happen. Because in this class, we want to see those wrong things happen because that's what we're learning about. Now, if you took out the sleeps, would it work? Maybe if you tested a few times, but it's not correct because it is possible with those things being concurrent that they could still overlap. All right, so we test it. After that, you should print out what you get or execute it, record the final balance. I kind of gave away the answer accidentally. A plot spoiler. But anyway, plot 2 here is analysis. So I want you to look at that code with those three processes. We're going to make a deposit process, a withdraw process, and a withdraw process. I want you to make 3 processes, each with those 3 kind of statements in them. So notice that this is get, subtract, restore. Get, add, restore. We'll ignore the log because that's not really changing anything, although logging to something at the same time could be its own separate problem. But think about it with 3 processes, 2 withdraws, 1 deposit. What are all of the final balances you could get out of this? What are all of the different, how many effective orderings are there? And how many distinctly different balances can you get? And I want you to list all of the distinctly different balances you could get. And the way to think about that is think about it as these values or transactions could be lost, because remember what happens if you get this value at the same time. One of them changes it, the other one changes it, one restores it, the other one restores it. They're kind of, it's that concurrent write update problem we talked about. One or more of these could be lost, but not all of them could be lost. So think about that when you're coming up with how many different balances there can be and what the list of them are. All right, concurrent execution and testing. I want you to create a thread for each one of the 3 method calls that we had up there, which, since methods of an object are still functions, you could pass the function, the object method to that thread.start. Remember, you're passing in this information here. To pass that in, you need to pass that in as an argument using the args equal when you create that thread using threading.thread. One word of caution though, and let me switch over to Python, the Python shell just for a second, and I'll explain that word of caution. When you have that args equal, so let's say I do thread1 equal threading dot thread, and I say target equal you're going to have something like that. Remember, don't put the parentheses here to do the function call. Don't do that. That's incorrect. We're just setting that up. But here I want to put args equal. And when you put the arguments in here, if I were to just do like 500 in parentheses, that seems right. But remember, putting a number in parentheses just is a way of grouping. So this is not a tuple right now. To make this a tuple, this seems a little weird when you first see it. Put a comma at the end of that list with nothing at the end. And that says, even though there's one argument in here, it's a list of arguments with just one. Whereas if I take that off, it's a number. That's a tuple. That's a number. So that's how you'd make it. I don't have an account, the class made or anything like that, but this would work if you made it an instance of that class account there. Now, just to show that that's a tuple, so if I do like 500, like that, and I say, well, what's the type of that? That's an int. What if I say, what's the type of 500 in parentheses? Still an int. But if I say, what's the type of a 500 comma, that's a tuple. So that needs to be a tuple. So even if you have one thing, you need to put that comma there. Okay, to finish this up here, you're going to then execute those concurrently. I want you to run the program, observe the output with 30 trial runs, and see if it's coming up with values that match what you thought it would. See if sometimes it's right. Sometimes it might produce the right answer. Sometimes it might produce things that are bizarre or have things that are missing. Okay, that's it for that assignment. So a couple things to finish up here. Hold on one second. Let me switch back to the presentation. Okay, so to finish this up, we looked at the assignment. If you have not used Python before, you're going to need to for this class, at least for a little bit. The good news is Python's a pretty easy language to learn. And also, if you don't have it installed, you can go to python.org and download it. If you have a 64-bit machine, which probably most of you do, get the 64-bit version, install it. That idle program will come with it, so you can just start idle, file new, write your code. Either go to run, or you could do F5 to run the script, give it a name, .py as the extension, run it. It'll work just like what we did when we wrote that there. So if you're new to Python, you might also want to look at my guide that I've posted to the course page called Python in a Couple Hours. And that guide I created to be a really quick, people who've already programmed before, a quick introduction to the kinds of things that Python can do and how to do them. And I purposefully didn't make that like a textbook and have it be really long and exhaustive. I basically just said, hey, I already know you know how to program. Here's how you make a for loop. Here's how you make variables. Here's how you perform some arithmetic operations. Here's how you do a while loop. Here's how you do if statements. So lots of little things like that, including things like lists and sequences and classes and stuff like that. But really, if you just have a couple hours and haven't learned Python before, go through that, install Python, go through and try some of the stuff as you go through and test those things. But that's it for now. Do that, get started on that assignment, work on your lab 1. You should really be able to get that done today. Other than that, stay safe, wear a mask, wash your hands if you go out. Yeah, wash your hands if you don't go out. Stay away from people not in your household unless you actually have to be around them. Work on that lab. And as always, let me know if you have any questions or problems, need any assistance. I'm always happy to help. All right, that's it for today.